ahead and get that balanced equation written down. And we'll start talking about gas stoichiometry. All right. So, does the word stoichiometry make you happy? Yeah. Usually a no. Okay, so what we're looking at stoichiometry, right, we're going to put quantities to this chemical formula. Okay, and we want to find out how many grams of, can anybody name that compound? Just aluminum oxide. Okay, good, because it's an ionic compound. Aluminum oxide. So how many grams of aluminum oxide are formed from 15 liters of oxygen gas at STP? Okay, so do we know a conversion factor between grams and liters? No. Not so much, right? But what do we know a conversion factor for? Yeah, we know moles to liters. And do we know how to go moles to grams? Yeah. Okay, so there's our moles is always our middleman. So we're going to use that Avogadro's principle, which tells us what about 1 mole of a substance at STP? 22.4 liters. Good. 22.4 liters. Okay, and that's only true at STP. Okay, so in order to do our stoichiometry conversions and our T-charts, we have to have a conversion factor between moles and liters, and we do. Okay, if it wasn't at STP, then we'd have to use the ideal gas law to get there. But with this conversion, it makes our T-chart really easy. Okay? So we're going to start with what we know, right? We know we have 15 liters of O2. Okay, and our overall goal is to be going to grams of aluminum oxide. But to get there, we need to go liters of O2 to what? Moles of what? We got to go moles of O2. We can't go to our other substance yet. So we would say 22.4 liters of O2 is equal to 1 mole of O2. Okay, so now I'm left in moles of O2. That's not what I want. What step has to go next? The mole ratio step. Good. Moles to moles. So I would go moles of O2 to moles of aluminum oxide. Okay, and where do we get these coefficients from? The balance formula. Good. So I would say 2 moles of aluminum oxide is to 3 moles of O2. Okay. I'm done with moles of oxygen. I've canceled all that out. Now it's going to be my last step, which goes moles of aluminum oxide to grams of aluminum oxide. Okay, moles always gets the 1, so we need to calculate the molar mass of aluminum oxide, which is why you need your periodic table. About 102, good. So now we've canceled all of our units. We're in the correct unit which that we need. So we're going to multiply across the whole top, divide by the whole bottom. What did we get for the mass of aluminum oxide? Good. Very good. 45.5 grams of Al2O3. Perfect. Okay, go ahead and try this one on your own. I gave you the balance formula. We want to find out how many liters of waters can be made from grams of hydrogen gas. So same stoichiometry setup, except kind of we're going from grams to liters this time. We're going to look at changes of state or changes of phase. Okay, so what does that mean in terms of a change of state? What does that mean that's happening? Exactly, solid to liquid to a gas, or gas, like, you're freezing, you're melting, doing things like that. Okay, so in order to be considered a phase or a state, those two terms are pretty interchangeable. it has to be part of a system that's uniform composition and uniform properties. So in order to be considered a solid, everything within that group has to have solid properties, has to be the same substance, okay, in order to be considered a phase. So I want you to go ahead and look on page 342, and this is a copy, I want you to copy this table into your book. It has to do with phase changes and the names that go with them. Some of them are extremely familiar, and some of them are a little bit less familiar. Okay, so if you know them, you don't necessarily have to put that whole table in your book, in your notes. You know, you kind of know what melting and freezing are. The other ones, I would go ahead and get probably those into your notes. Each of these, okay? So condensation is when gas changes to a liquid. When do we see condensation happen? On your cup, right? So what's happening with that cup of liquid, right? When does that happen? When? Try to describe to me what's happening there. Yeah.
Like the cup is cold and the air around it is hot, so the cup cools down the gas in the air.
Perfect. Does it happen when our cup doesn't have ice in it, or when our cup water is not cold? No, it wouldn't happen if our liquid inside that cup was not at a colder temperature than our air. Right? If it was already at room temperature, we don't see condensation anymore. We see condensation when we have the solid form or the ice or the colder form at least moving to that liquid form. So when something goes from cold to hot, we'll see that liquid we'll see the gas go to a liquid state. Okay, so if we see a gas changing to a liquid, do we think that object is heating up or cooling down? If we see condensation happening, do we think that liquid, or do we see that object getting hotter or colder? Yeah, hotter. It's getting hotter. Okay, because to go from a gas to a liquid, we've got to put energy into that, right? That temperature has to increase to go from a gas to a liquid. Yeah. Okay. You guys had me doubting myself for a second. Okay. Yes. Yeah, it means violent. Violent. That's a good one. Volatile liquids mean they're unstable, right? They're crazy. Okay, they're the outliers. So volatile means pretty unstable. And volatile liquids are ones that have weak intermolecular forces, and they're going to evaporate really quickly. Can anyone think of examples of a volatile liquid? Alcohol would be one. Acetone, that's a really good one. Where do you see acetone most commonly? And nail polish remover. So if you ever spill nail polish remover, you'll see that it dries up like almost instantaneously. Okay, that's a really good example. Gasoline is another one. That's a volatile liquid. Those are things that evaporate really quickly, like rubbing alcohol. Those are all things that evaporate quickly. Okay, anything else? Okay. So if they evaporate quickly, let's say at room temperature, acetone evaporates at room temperature, right? That's enough heat to cause it to evaporate. So you just have to cool it down just a little bit to get it back to that liquid state, right? Do we see that kind of difference there? If it evaporates at room temperature, you only need to cool it a little bit to kind of get it back to that liquid state. All right, so we talked about condensation. Now boiling is very familiar to us, right? We're going to go from a liquid to a vapor state, which means we have to add energy to that. Okay, so I'm not going to get confused on this one. I'm not going to try to confuse you. Okay, if you add energy, we see that these gas particles, the liquid particles heat up and heat up and heat up, eventually breaking those intermolecular forces and becoming gas particles. Okay. Again, these are things that you're probably pretty familiar with. You don't have to write them down word for word. Okay, I'm going to go through this pretty quickly, so just write down what you absolutely need to. Okay, the boiling point is very specific to each compound. Each compound has its own boiling point, and the boiling point is so specific it's used to identify unknown compounds. Okay, so you can melt down an unknown compound and get it to a boiling point, and that can help you identify an unknown, right? The boiling points are so specific. And so a boiling point is the temperature at which this equilibrium vapor pressure equals the atmospheric pressure. It's this point in which we've reached this complete equilibrium between vapor and liquid. Okay? So we'll reach that point. And it's identifiable to that specific compound. Okay? The lower the atmospheric pressure, the lower the boiling point, and vice versa. Okay, lower the atmospheric pressure, the lower the boiling point. Okay, that's why, have you ever heard like that things cook different at different atmospheric pressures or at different heights or sea level? Have you ever heard that? Things cook differently at different altitudes. Yeah, things. Water boils at a different temperature, like in Denver, than it does here. Okay, it's not by a whole lot, but it's a little, right? They have different atmospheric pressures, so that's kind of the reason.
So then is boiling point based on like sea level?
Yeah, very loosely, but yeah, it would change. I don't even know, maybe only a couple degrees, if that. But yeah, it's got to be that point in which our atmospheric pressure matches our vapor pressure. Okay, at the boiling point, all energy used to evaporate liquid is a vapor gas state. The temp remains constant as long as the pressure doesn't change. Okay, so once we reach the boiling point, we're at this kind of equilibrium where our gas particles float up. If they get high enough away from the heat and they cool down again, they'll come back down. You don't really see that happening in your kitchen too often. You don't see it raining, while you're boiling water, but you'll see them start to maybe condense up on like the hood of your stove. Have you ever noticed that? When you're boiling water, you'll have maybe some condensation up on the hood. That's because by the time those gas particles get that high, they start to cool down again, and they'll start to form water droplets again. You usually don't see it raining back down, but you might see a little condensation up there. Okay. All right, boiling point increases in molecules with strong intermolecular forces. Hopefully that's self-explanatory because we know kinetic theory, that the stronger the intermolecular forces, the more heat it requires to break down those forces, which means a higher boiling point. Okay, it would also mean a higher melting point. We consider freezing to be a removal of energy, right? We're losing energy in that system. We're cooling it down, so we're losing energy. That's all we really need to know about freezing. Okay, hopefully that's a little self-explanatory. Sublimation is now going directly from a solid to a gas. Okay, and dry ice is the most common example of this. Can anyone think of any others? Going directly from a solid to a gas? Not so much. No. I mean, you might be able to come up with a few. Dry ice is the most common example. Okay, directly from a gas to a solid. And I want to see if anybody can come up with when this might happen. Snow's a good example. Snow is a good example. What happens to your car when it's really cold outside? You get frost on the windshield, right? And does that frost come in form of water droplets? No, it's a more like crystallized, right? That means we've gone directly from those gas particles in the air, those water vapor in the air, to that solid state on your car. Because if it went to the liquid state, we would see it in little water droplets, and it's rare that we see it in that form, right? It's more of that crystal state. Another one would be if you, when you can see your breath, right? Those are water vapor that's kind of being solidified a little bit, but not necessarily to water droplet types. All right, so again, we see that going directly from our gas states to a solid phase, a little bit more common, okay? Okay, those are all the ones that we're going to talk about in terms of phase changes. There's a few more on your table that you might want to be familiar with, but that's pretty much it for what we're going to go over. We're going to look at a phase diagram next, and we're going to look specifically at the phase diagram of water. Okay, and what a phase diagram does, it gives us the specific conditions in terms of pressure and temperature in which these phases would exist. Okay? So let's think about water for a little bit, and let's get on terms of Celsius temperatures. Okay, what's the boiling point of water in Celsius? 100. Okay, and what's normal atmospheric pressure for us? What's STP? 1 atmosphere. Okay, on any given day, the atmospheric pressure is at or around 1 atmosphere. Okay, so if our water boils at 100 degrees Celsius and our pressure is usually about 1 atmosphere, what state would our water be in, solid, liquid, or gas, if it was 56 degrees Celsius and 1 atmosphere pressure? Would it be a solid, a liquid, or a gas? 56 degrees Celsius. It would be a liquid, right? What's the freezing point of water in Celsius? 0. That means so from 0 to 100, as long as our pressure is reasonable, we've got a liquid. If it's at 115 degrees Celsius, what state would we be in? A gas. Okay, so we're going to look at a phase diagram. It's a graph that shows us where these lines are, these equilibrium lines between gas and liquid, between liquid and solid, things like that. Okay, so we're going to look at the phase diagram of water, and I'm going to give you this diagram to look at. So this is for you to keep, so I hole punched it. And we're going to do some labeling on this diagram. So let's talk about this label. We're going to start first with letter D in the middle. Do you see that letter D? Yeah. And what do you notice about D?
It's right where the 2 lines line up.
Yeah, it's right where the 2 lines, realistically, all the 3 lines intersect. Okay, but that's okay. We call it the triple point. Okay, so you can either write that on here or you can write it in your notes. Either one is fine. Okay, probably on the diagram would make most sense, but it's called the triple point. Okay, and then if you want to put the definition in your notes, you can, because definition you might not have room on there. But letter D is called the triple point. And what it means is at this point, these specific conditions, 273.2 Kelvin and 0.006 atmospheres, at those exact conditions, water can be both solid, liquid, and gas. Okay, it can be all 3, which is why we call it the triple point. Okay? It can be solid, liquid, and gas at this point. Okay, so if we're at this strange set of conditions, right, that's extremely low pressure, and extremely low, and not that low temperature, a little over boiling point, I guess. So at very, very low pressures, we can see this water exist at all 3 phases. Okay, so that's why we call it the triple point. you will need to be able to label and predict states of water based off this phase diagram. Okay, so like on your test, you could expect a diagram like this and tell me, what state is it in at these conditions. That's the type of stuff you're going to have to be able to do with this. Okay, and other phase diagrams too. Every compound has its own phase diagram. Water's just the most common. Okay, so the critical point is what we label at point E. Okay, we call that the critical point. And at the critical point, we've reached this point at which we're at such high pressure and such high temperature that we can no longer exist at a gaseous state. Okay, water can no longer exist at a gaseous state. Okay, so what do you think happens to it after that? I don't know, somebody Google it.
Would the hydrogen break away from the oxygen?
I don't know.
It disappears.
Google it. For a supercritical fluid, for critical point on water, they're labeled on your chart as well. You just might want to point them out. I think the temperatures on your chart got cut off, so if you want to add those in, you can. They're up here on the diagram on the screen. Okay, I'm pretty sure that the temperature got cut off on your graph, so if you want to add those to the bottom of your chart, that's probably going to be helpful. Sublimation and deposition. Those are the two. Is that what you said, deposition, right? Okay, yeah. Those are the two things that go between a solid and a gas and a gas and a solid. So those would occur along this equilibrium curve of A. Okay? So this is the temperature and pressure conditions at which gas and a solid can exist simultaneously, okay, at the same time in equilibrium. So that means at any point along this curve, right, we could have a temperature, we could have a temperature here and a pressure here. That would be along the curve. We could have temperature here and pressure here. That would be along the curve. Okay, so anywhere those two conditions meet along that curve, we would have equilibrium. If I had a temperature of, let's say 100 and a pressure about right here, what condition would what state would I be in? Solid, yeah. If I had low pressure and I had 100 temperature, I'd be in the solid phase, right? So they might not always meet along that line. Those are just the conditions at which would mean an equilibrium between those two phases. Okay. So that means curve B is probably what equilibrium line? Between solid and liquid. Okay, so temperature and pressure conditions in which ice or solid and liquid water can be at equilibrium. Okay, so what happens along that line? What two phase changes? Melting and freezing. Good. Melting and freezing. Those two things happen along that equilibrium line. Okay, very good. All right, and what do you think the last curve represents for us? Between gas and liquid, right? It's our equilibrium curve between gas and liquid. And what phase changes occur along that line? How do you go from a liquid to a gas? Vaporization and condensation. And vaporization is like boiling, right? So boiling or condensation would happen along that line.